He kōna I purangi tēnei nā te reo irirangi o Aotearoa.
Kia ora, nā mai haramai ki te ao hurihanga. Hello and welcome to Our Changing World, ko Concannon tēnei. Last week we headed to GNS to learn about Te Puna Mōrere I Teru, the National Geohazard Monitoring Centre, where a team are on alert 24/7 for any geohazard events.
98% of the time we're in a state of business as usual, but for that 2% of time there's an element of readiness because we will have to respond rapidly.
This week, we dig into some of the research behind our understanding of the hazards Aotearoa faces. Later, we learn about the massive effort to 3D scan part of the Hikurangi subduction zone off the east coast of the North Island.
To try and understand the physics of the earthquake behaviour, the slip behaviour, we need to obtain information at a very detailed resolution.
But first, we're all aware of the damage that landslides on Earth can cause. But what about those that happen out of sight?
Landslides can happen underneath the sea, much the same way as they happen on land, but when they're beneath the ocean, they can be many, many times larger than the ones that we see on land. And so, for example, we know that some of the biggest underwater landslides can move as much sediment or material as, for example, all the world's rivers move in 1 year. And so all that kind of equivalent volume can be moved in one big underwater landslide event.
This is Dr. Suzanne Bull, a senior marine geohazard researcher at GNS. And obviously, that's a lot of sediment to move in one go. But if it happens out in the ocean, so what?
The biggest hazard is the potential to generate tsunami. And so when you disturb the seafloor to that extent, if it's a really large underwater landslide, you can generate a tsunami that can impact coastlines. But then there are kind of other things to consider. You know, the more infrastructure we put into our oceans, whether it's pipelines or telecommunication cables, wind farms, etc., the more we need to know about these kind of dynamic processes that can affect the seafloor. And so if you happen to have a cable or a pipeline on a part of the seafloor that then moves in a landslide, you can cut off your internet or you can, lose your pipeline. So there's kind of different scales of things to look at.
Like on land, anywhere that you have a decent slope, there's the potential for a landslide. But what might set them off?
Some landslides are triggered by what we would call a dynamic or instantaneous trigger, like an earthquake that would shake the ground or the underwater slope, but also things like loading through extreme weather events, whether that's storm events. You have a lot more wave action that can move sediment around and destabilise some slopes, or extreme weather events such as we were recently affected in New Zealand by Cyclone Gabriel, and we all saw the images of the sediment and the silt that was washed down the valleys in that event. And of course, that will eventually end up in the ocean. So that can also load slopes and lead to failures. But in truth, we don't have a huge amount of data firmly linking underwater landslides to any trigger in particular, because it's just so hard to survey the offshore environment. It is, expensive and time consuming. And so we're not able to replicate a science response. If there's an earthquake, we go around and we survey the landscape for landslides onshore. We just can't do that offshore. It's too resource expensive. So we're not able to link landslides and distributions of landslides, like how many and how big, to a particular event, like a magnitude 7 earthquake, for example.
I see. So something like Gabrielle, you've got this big flood event, and then afterwards you've got reports from people, you can fly a helicopter over, you can take images, and you can essentially count the landslides. You can see them there and you can see the scale of them. And this is just not the case under the ocean.
Yeah, exactly. So, I think over about 140,000 landslides have been documented in the aftermath of Cyclone Gabriel. And then if we think about the Kaikoura earthquake in 2016, I think there were around nearly 30,000 onshore landslides documented. So what you've got is this incredible data set linked to a particular trigger. And you're exactly right, we cannot replicate that offshore.
Out of sight, but not out of mind. Scientists are certain that underwater landslides are happening. Their aftermath has been spotted in lots of places.
All around the world, particularly on continental margins. So those are the parts of continents that slope away from land down into the deepest part of the ocean. They're a very common place for underwater landslides to form. So we know of, hundreds, thousands of examples that have happened. But what we don't know so much is exactly when they've happened and how often they happen.
One we definitely do know the timing for occurred in the late 90s with devastating impacts.
In 1998 in Papua New Guinea, that was the event that really changed the way scientists looked at underwater landslides and their hazard potential. And so in Papua New Guinea, there was an earthquake that happened offshore. It was around a 7 magnitude, so it's not a small earthquake, it's not a huge earthquake either, but because of the nature of the faults involved, the understanding was that it wasn't the kind of offshore earthquake that was likely to generate a tsunami. But I think then within 15 minutes of the earthquake, a tsunami did inundate part of the coastline in a kind of low-lying lagoonal area, and unfortunately did lead to many deaths.
It's 20 years since a horrific tsunami struck part of Papua New Guinea's West Sepik province, killing about 2,200 people. Waves estimated to be as high as 14 metres washed across Sasano Lagoon, where most of the deaths occurred. It was originally thought to have been caused by a 2-metre drop in the Pacific plate after an earthquake, but now it's believed it was instead caused by a massive underwater landslide.
It just didn't make sense that the earthquake that had happened could have generated a tsunami such as was observed. And so then, of course, there were seafloor surveys done and numerical modelling to try and understand the event that had actually happened. And it was concluded that it was most likely caused by an underwater landslide that had been triggered by that earthquake. So it wasn't a particularly tsunamigenic earthquake, but it was enough to trigger an underwater landslide close to the coast, which then, again, without any way of knowing that's what had happened, the tsunami that then did inundate the coastline was quite unexpected, and there wasn't decisions made about evacuations and things like that. So it was an event that, I guess you could say the world wasn't prepared for, but we, at that point realised the hazard potential of landslides and what could happen. And so that's really what we're trying to understand better. Like, is there any potential for that around New Zealand? And if so, where? And what should we be doing about it to keep communities safe?
It's a big task because, well, they're underwater. Colleagues of Suzanne's at NIWA are currently using existing seafloor map data to look for evidence of landslides around New Zealand. This will give an idea of where they've happened in the past, highlighting where they're more prevalent. But Suzanne and her colleagues have also found and honed in on 6 really big underwater landslides in the Tasman Sea, off the west coast of Te Ika Maui, off Taranaki.
We discovered them when we were mapping the offshore geology around New Zealand, so we kind of stumbled across them in a sense. But once we had mapped them and identified them, we naturally had some questions. Why did these form here, and when, and how frequent are they, and what are the potential hazard impacts of them? And so to study them, we've had to go out using a science research vessel. And so you're out on a ship that's equipped with equipment to map the seafloor and also to collect sediment samples. So you have coring systems, which is essentially like a long barrel that's lowered to the seafloor and sinks into the sediment. And so what you recover is like a long tube or cylinder that preserves the layers of sediment and stratigraphy below the seafloor, youngest at the top, oldest at the bottom, and you can start to unravel from that. Okay, well, I have a landslide unit that occurred at this point in time, and underneath that is another and another. And you can start to, we sometimes call that sediment record the Earth's tape recorder, kind of things that have happened in the distant past before we were around, before we had instruments to record geological processes. We rely on the sediments to kind of tell us the story of what's happened to the Earth.
And the biggest one they've discovered so far is buried beneath the modern-day seafloor.
At the moment, we think it happened around 1 million years ago. I say at the moment because we've collected some sediment samples and we're in the process of kind of crunching through that information to try to understand better the date of when it actually happened. It covers an area of about 22,000 kilometres squared, so that's a little bit bigger than Wales. And then in terms of volume, it's around 3,200 kilometres cubed in volume, which is kind of, might not mean anything to people. I mean, it's a little bit of a hard number to get your head around. Most people can picture Mount Ruapehu in their heads, and that's about 100 kilometres cubed in volume. So I didn't work that out, but some clever volcanologists did. And so I tried to imagine, 32 Mount Ruapehus just sliding down the slope 1 million years ago. And so at the moment, that's what we know in terms of its kind of size. And then what we're trying to understand from that is what are the potential hazard impacts from it. So is that the scale, a kind of scale of a landslide that could generate tsunami? And some very initial numerical modelling studies we've done suggest that, yes, it could. It was a very large volume of sediment that kind of was displaced downslope. And so it was likely did generate a tsunami that probably impacted the northwest coastline of New Zealand. And thankfully, no one was, or we weren't here at the time to experience that. But of course, the next step for us is trying to understand if there's any potential for another landslide like that to happen in future, because if there is, then obviously we need to think about what we need to do to prepare for it.
Nobody has specifically looked to see if there's evidence of this landslide-induced tsunami from 1 million years ago. And New Zealand has changed a lot since that time. Part of the coastline where you might have expected the tsunami to impact have either been eroded or uplifted, erasing the evidence. But people have looked and found this evidence for a different underwater landslide.
Probably the most famous example, and of course I mean within the kind of, geeky circles of people that study underwater landslides. But yeah, we have this example of the Storegga slide offshore Norway. So that one happened around 8,000 years ago. And what that means is, that's not all that long ago in geological terms. So when you map the seafloor, it's still quite fresh, if that makes sense. There's still quite a fresh scar. So huge scar. I think the head wall scarp of the landslide is about 400 kilometres wide. I think Storegga in Norwegian means great edge, but I was going to say, don't quote me on that. But if so, it's a very good name.
Can confirm. This is what it means.
And it just so happens there have been energy resources discovered beneath the slide. And so there was a lot of information collected to understand, is it safe to extract those resources, or do we need to just leave it alone, essentially? And so it's probably the best studied and the best dated. So we have accurate age information. And one of the most interesting things about Storegga slide is that there isn't a lot of tectonic activity in that region because, we talked earlier about what could trigger it. And I think we often feel as if there has to be a big, very strong trigger to create an event like that. But this is a region where there's very little seismicity or ground shaking. And so, what's the trigger then? If not an earthquake, a big earthquake. But it's very strongly linked to climatic kind of cycles because of the way the different layers of soil and sediment form offshore made that part of the Norwegian shelf quite unstable. But what's really valuable about that example is that we know how big the landslide was. We have a fairly good understanding of how it formed. Did one little bit go first and then the rest, or did it all go in one go? But it's also linked very strongly to tsunami deposits around the region. So we know that there was a regional tsunami that affected, the Norwegian coastline, but also the mainland of the British Isles and the Scottish Islands, and up to 20 metres run-up height in some areas, so a very decent tsunami. And again, those tsunami deposits, so the geological evidence for this tsunami, have been very well studied and dated. And what that does is it kind of gives us a data point, and so looking at these giant underwater landslides in New Zealand, we've done some preliminary numerical modelling, and it suggests that the biggest one that we're studying offshore of the North Island could have generated a fairly big tsunami. And Storegga gives us this ability to say, well, is that ridiculous? And you can say, well, no, it's kind of what we saw from the Storegga slide. And Storegga is very similar in size to the landslides we're studying in New Zealand. And so it really gives us a nice bit of constraint, like almost first sense check, and say, well, what did we find? And, oh, wait, you could say, wait a minute, that was like way off the scale. Storegga slide, we only had this. So it kind of brings us back to a real world point that we can use to sense check what we're doing.
This modelling is what they're working on now for that 32 times Ruapehu landslide off the Taranaki coast. Once they've identified the past landslide and then got the information they need, things like how big the landslide was and how much material was involved and what water depth it happened at, they can then feed this into a hydrodynamic numerical model. This type of model predicts how fluids behave, and so the landslide is treated like a very dense fluid.
So we almost like reconstruct the landslide in the model. We model its movement, and as the landslide is moving, it's underwater, so it's then displacing water above it. So we tend to couple the motion of the landslide to the water column above it. And after that, we then model the way that any waves that have been generated, how they propagate and arrive at coastlines. So it's quite this complicated, like several steps. And it's this interesting fusion of like marine geology as a science discipline, fusing with fluid mechanics, which is quite a different language. And you need a multidisciplinary team. And we talk about the science value chain. So you almost like someone has to do the first bit and then you pass it up to the chain to the next person. And we're working here in the realm of kind of science understanding. We're trying to understand the hazard so we can then progress it down the science value chain to kind of hazard understanding and quantifying the hazard. Because this is actually really important for emergency management planning. You have to be able to deliver certain information. And we tend to like things to be expressed in human timescales. So we might want to know, what's the likelihood of a landslide happening? You say, oh, well, this was a 1 in 100 year event, or we're not likely to have an event like this for another 10,000 years. Because once we put the information in those terms, we can actually use it to make decisions and plan for hazards actually happening.
Thanks to Dr. Suzanne Bull, Senior Marine Geohazard Researcher at GNS. And now we move to the other coast to find out about a massive project to better understand the potential hazards lurking off there, hazards linked to the Hikurangi subduction zone.
That is the zone where the Pacific plate, that's made up of most of the ocean in the Pacific, is subducting or diving down beneath the North Island of New Zealand.
This is Dr. Stuart Henrys, a principal scientist at GNS with a focus on marine geophysics.
So the North Island is situated on the Australian plate, and the Pacific plate is diving down beneath the Australian plate along a line that stretches from just north of Christchurch all the way to Tonga and up to Fiji. What we refer to as a Hikurangi subduction zone is that part that is mainly off the east coast of the North Island, and then it changes its name. It's like a street. Changes its name north of East Cape to the Tonga-Kermadec subduction zone.
It's easy to get lost in the science, and we're about to do that. But just take a moment here to think about how immensely cool and massive and crazy this is. One huge continental plate, the Pacific plate, is diving underneath the Australian plate. Think of the forces at work here, the energy that must be involved. The Earth is wild.
So that is a zone of friction and can create large earthquakes. So that kind of subduction zone, it rings the Pacific, Chile, North America, Japan, all the way down to Philippines, parts of Indonesia, and to New Zealand. So that's a zone where the largest earthquakes have occurred. Chile, Alaska, Sumatra, Japan, Tohoku in 2011. And so potentially in New Zealand, it could be subject to very large earthquakes as well.
And because of the nature of this subduction and because it's underwater, these earthquakes are likely to cause tsunamis, such as the 9.1 Tohoku earthquake in Japan in March 2011, which created massive tsunami waves, resulted in the loss of close to 20,000 lives, and caused the Fukushima nuclear accident.
A catastrophic tsunami rising out of the Pacific. Its huge waves sweeping away everything in its path. A massive wall of water that rose as high as 30 feet, swallowing up parts of Japan.
I don't know if you remember this at the time. I certainly do. There were so many mind-blowing videos of this horrific destruction wrought by these huge waves flooding coastal communities.
In Kesennuma, people retreated to a high-rise rooftop and could only watch in horror as tsunami waves inundated their city, knocking buildings into rubble and mixing into a kind of tsunami soup filled with vehicles, building parts, and contents.
These large megathrust earthquakes occur when friction that is built up at the plate boundary is suddenly released. But if everything is sliding nice and smoothly, then it should be fine, right? The Pacific plate just glides under the Australian. So what do we know about the nature of this Hikurangi subduction zone? Are the plates smooth or sticky?
The slip behaviour on the plate boundary is quite different in different places. So, for example, offshore Wellington, we know the plates are locked, so that means they're not moving past each other. And we know that because we can put out GPS sensors on shore, and we can see that over time, just subtly over years, that movement is not great. And we know that because we can measure the movement of the plates in millimetres. So in contrast, the area to the north, so from Hawke Bay northwards, is not locked, it's unlocked, and so that means it's slipping past each other more smoothly. However, there are places where it is not as locked, but it's not slipping and creeping, it's behaving in a very odd way. So this is the zone where we can detect slow slip. So that's earthquakes, but they occur over weeks, months. So the plates are not rupturing in events that you can feel, but nonetheless, they're still behaving in a way like earthquakes. Slow slip earthquakes, we call them.
Using GPS sensors on the seafloor and on land, they've been able to determine that slow slip earthquakes in this area occur pretty regularly, about 2 years apart. And there's a lot of international interest in them.
Prior to the 2011 giant earthquake in Tohoku, slow slip was measured. So that everyone was very excited by that. You know, what's going on? Could slow slip be a forecast tool for giant earthquakes? And so other nations, the US has subduction zones along its west coast. Japan, very much like New Zealand, subject to subduction zone earthquakes. Why Europe? Well, the Europeans also interested in hazards. They have subduction zones within Europe. And, you know, really interestingly, the physics of trying to understand the earthquakes is a challenging global problem. It's a human problem, societal problem, and we need the resources of the international community.
And that's what happened. These slow slip events offshore of Gisborne are the world's shallowest, which is why international resources were pooled to do a 3D scan of part of the area. The Niwa research vessel, the Tangaroa, was used to put Japanese instruments on the sea floor. Onshore instruments belonging to the UK were put out along the coast, and a US ship did like a racetrack loop around and around the area, towing another array of sensors. The idea was to create detailed images of the layers beneath the seafloor, where the subduction is happening, using sound waves. The ship sent sound energy down into the ocean, and the echoes that bounced back from the layers in the earth were recorded on the 3 sets of sensors, those on the seafloor, on the land, and towed behind the ship.
So it was a big experiment, collected a huge amount of data, an enormous amount of data. It took us nearly 3 years to process that and create a kind of CAT scan image, something that, you know, you would get within a few minutes of putting yourself in a scanner. So it took us a great deal to take that data and create the slicing and dicing of a 3D volume in order to understand what's going on inside the subduction zone.
Remember, the whole subduction zone is large. Starting off the north of the South Island, it runs all the way past Tonga, about 3,500 kilometres long. So they scanned just a teeny part of it.
We concentrated our work in a narrow corridor, so 16 kilometres out from Gisborne, just north of Gisborne, to across the plate boundary, across the Australian plate, across the trench that marks the boundary between the Pacific and Australian plate, and then a 15-kilometre wide corridor. So a tiny postage stamp area, but an incredible amount of detail. And that area is where the slow slip has been mapped offshore by GPS.
This is the same area where 2, as Stuart refers to them, biopsies were taken in 2017 and 2018. A scientific drilling ship bored into the seafloor to collect sediment samples in the area. So they've spent years analysing the data, and now results are being published. What have they been finding?
The big finding from the 3D data that we collected is a better understanding of a seamount. So the Pacific plate is not smooth. It's a complicated piece of crust. It's quite thick, and the thickness of the crust gives you the buoyancy that makes the Hikurangi subduction zone kind of unique. But dotted on the Pacific plate are these seamounts, and they've been pulled under the rug as part of the plate boundary process.
Okay, so we look at a geography book and we see, this nice curve drawing of one plate going down under another, and you're like, no, it's not like that.
It's not like that. It's not two bits of carpet sliding past each other. We're trying to shove a big rock under the carpet in the Hikurangi, and there are lots of these seamounts dotted on the Hikurangi Plateau, we call that, on the Pacific plate, that is trying to be subducted. So that interaction between a seamount and the overlying plate, the Australian plate, creates a lot of heterogeneity, creates a lot of complexity. And you would think that actually that might be a place where you could get earthquakes. It's an asperity. It's something that would stick and slide and create some friction. Well, no. It turns out that the seamounts actually might preferentially be places where you get slow slip, or slow slip around the seamount, and then on the core of the seamount they might contain fluids. And so it's that interplay between the roughness, the seamount, and the fluids contained within the seamount that's been subducted that might be generating slow slip. So that's one of the complexities. The other is that in the wake of the seamount going down, you can think of the rock and the rug again. So in the shadow of the rock, as it tries to get beneath the carpet, is sediment that is undisturbed but contains a lot of fluid, and that itself may be enhancing slow slip. So it's a complicated process. We know that seamounts are part of the process that creates slow slip. We know that they may contain fluids, and that fluid pressure at the subduction zone may enhance slow slip.
If you, like me, are thinking of these seamounts as little pimply rocks, then think again. The seamount they're looking at is 2 kilometres high, 50 kilometres wide, and 10 to 15 kilometres long. So it's large. And seabed mapping shows that there are others dotted around, some bigger, some smaller. What they're working on now is more of the details of the interaction of the seamount and the rocks that sit above it, the Australian plate rocks. And this is cool and all, but how does this help us?
What we can use from the results of our study is, even though it's a small patch, we now have a better understanding of the physical properties of the plate interface, and also the properties of the Australian crust that sits above the seamount and plate boundary, and also the crust that is subducting. So we can use that information to help build models of the subduction zone, of which we can use to create simulations of earthquakes. So having more understanding of the physical properties in finer detail means that the simulations will be more accurate.
After that, well, of course, there are even more questions to answer.
We'd really like to move south to understand offshore Wellington, where the plates are locked. So what's going on there? Is it the smooth interface where there are no seamounts, or they're buried very deep, and maybe it's not like a carpet, maybe it's more like a mattress, so it's buried deeper. What's the process that is causing the locking there as opposed to the slow slip and unlocking to the north? So it's that contrast between the regions, and what's happening in between. So what's happening off Hawke's Bay, where we transition from one type of slip behaviour to another? So these are the things we're trying to understand.
Thanks to Dr. Stuart Henrys, Principal Scientist at GNS. This episode was produced by me, Claire Concannon, with help from Justin Gregory and Ellen Rikers. Sound engineering was by William Saunders, and Tim Watkin is executive producer of podcasts and series at RNZ. Our webpage is at rnz.co.nz/ourchangingworld, and if you've got feedback for us, you can email ourchangingworld@rnz.co.nz, or find us on Facebook, where we are at RNZ Science. Tēnā koe I whakarongo mai. Thanks so much for listening. Ko Claire Concannon aho. Have a great week. Kia pai te wiki.